In section 9.2, we're going to do hypothesis testing of the mean under two different conditions, under the standard normal distribution or under the student's t-distribution, and which one will depend on our knowledge of the standard deviation of the population, in particular whether we know it or not, the nature of the x distribution, and our sample size. So we're first going to look at the conditions in which we will use the standard normal distribution, z. Later we will look at examples of the student t-distribution. So for right now, let's look when we use the standard normal distribution. Okay, so this is how to test mu when sigma is known, our standard deviation of the population is known. So let's read the requirements and then the procedures. In the requirements, we're going to let x be a random variable, and we're going to take a simple random sample of size n, and we're going to use our sample mean x bar. So we are assuming that the value of sigma is already known. So if you can assume that x has a normal distribution, that's great, because if x has a normal distribution, then so does x bar. So any sample size will do. If we don't know about x's distribution, then we're going to use a sample of at least 30. Both of those conditions, x has a normal distribution or a sample size of at least 30, those both imply that x bar is normally distributed. Okay, so that's what we want. Why do we want x bar to be normally distributed? Because then we can use z, our normal distribution. Okay, so what are our procedures? The first step is we're going to state our null and alternate hypotheses and our level of significance alpha. Our second step, we're assuming that we do know sigma, the sample size, okay, the value of, I will say, x bar from the sample. So let's see, and we're going to use the mu from our null hypothesis. We compute our z just as we would for any sample mean x bar. And then we're going to use a one or a two-tailed test, depending on whether our null alternate hypothesis is an inequality, one-tailed test, or it's just not equal, in which case we'll use a two-tailed test. Then we take our probability, our p-value, from that test to conclude whether or not we're going to reject the null hypothesis. If our p-value is smaller than alpha, then we reject, smaller than or equal to alpha. So let's look at an example. So let's look at this example. Let x be a random variable representing the average number of sunspots observed in a 4-week period. A random sample of 40 such periods from the Spanish colonial times gave the following data. Okay, so each of these represents an average over 4 weeks. So in one 4-week period, there was an average of 9.4 sunspots observed. In another 4-week period, there was 104 sunspot average. Okay, so let's see. So each of these data is an average. We have 40 of these samples. Okay, so our sample mean of x bar is 47. So if we were to add up all of these and divide by 40, we would have 47. Previous studies of sunspot activity during this period indicate that the standard deviation is 35. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about 41. So this is our historical claim. that the mean is 41. So let's read the last paragraph. Sunspot activity above this level, above the mean of 41, may or may not be linked to gradual climate change. So the question is, do the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? And we're going to use a level of significance of 0.05. So let's read the question. Is asking whether the mean was higher than 41. So it's asking, is there evidence that the mean is greater than 41? And we'll want to note our level of significance. Okay, so let's run through our 5 steps again. We're going to establish our null and alternate hypotheses. We're going to check our requirements. Make sure that we know why we will be using the normal distribution, or whether we should in fact be using the student's t-distribution. And we'll compute, once we know whether it's going to be z or t, we'll get our test statistic. Then we do our 1 or 2-tailed test to find the p-value. Then we decide whether we're going to reject or fail to reject our null hypothesis, and then we'll put our conclusions into a meaningful English sentence. Okay, so for our null and alternate hypotheses, we're going to use that the null hypothesis is that mu equals 41. The question is asking us to ask whether it was higher. Okay, so we want to know our alternate hypothesis is going to be, is mu actually higher than 41? So we're going to check our requirements to see whether we're going to use z or t for our test statistic. Well, we had a sample of 40 periods. So n equals 40, that is larger than 30, so we know that x bar is normally distributed. We also know sigma. So we're going to use the normal distribution for x bar. Okay, so we had a large sample size, and we know sigma, so then we're going to use the standard normal distribution. So our test statistic will be a z-value. And here we have the computation right here at the bottom line. So you can pause the video and see that you get the same value using your calculator. So x bar was 47. That was the mean of the sample up here in the body. 41 was our historical average, our mu. And then sigma was our mean that we were given of the population, and our sample size was 40. So our z-value, our test statistic, is 1.08. Okay, so our z is 1.08. So now what are we going to be doing to figure out our p-value? So to find the p-value of the test statistic, we're looking back at our alternate hypothesis. Our alternate hypothesis says that mu is greater than 41. If we have just greater or just less than, we're going to use a one-tailed test. So we're looking for the probability that here is mu is 0, here's 1, so here's 1.08. We want to know what is the probability that we are at least 1.08 standard deviations away above the mean. So at least 1.08 standard deviations above the mean. So our p-value is going to be the probability that x bar is greater than or equal to, what was our x value, x bar, 47, 47, which is the probability that z is greater than or equal to 1.08. To find this value, we need to use our z-table, And you have two options, of course. You can do 1 minus the value you see on your table, because of course we're looking for to the right of or greater than a value, and our table tells us left. Or you could look up the opposite. You can look up the negative. Z is less than or equal to negative 1.08. So you can do either way. So we're going to use so now let's look again at what the slides actually say. Mu is greater than 41 is our alternate hypothesis. So we're going to use a right tail test, yes. And here's our actual p-value. Z is greater than 1.08. So if you look up 1.08 on your Z table, this is what you get. We want to use greater than, so we use 1 minus. Or you could have looked up negative 1.08. So this probability is 0.1401. So there's a 14% chance that you would have had a Z value of at least 1.08. Okay, so to conclude the test, that means we have to decide whether we're going to reject our null hypothesis or fail to reject our null hypothesis. So we compare our p-value and our alpha. Our p-values on the left, alpha is on the right. So this says 14%. So there's a 14% chance of getting a mean which is at least 47. So that's not so small. That seems fine. So there's not enough reason for us to change our claim about the mean. So we're going to stick with that the mean is 41. We fail to reject the null hypothesis, meaning we don't reject it, so we're sticking with our null hypothesis that the mean is indeed 41. We don't have enough evidence to change it. So let's interpret our results in the context of the problem. So in the blue sentence here, at the 5% level of significance, the evidence is not sufficient to reject our null hypothesis. Or based on the sample data, we do not think that the average sunspot activity during the Spanish colonial era was higher than the long-term mean. So the blue sentence is a rather generic result statement from the data, and the sentence in black here really makes it specific to this particular problem. Okay, so that's our example when we're looking at testing with the mean. So now we're going to look at testing the mean when we may have to use a student's t-distribution.